Hi everyone, welcome to Power Electronics session 16. So far we discussed about all the inverters starting from single phase average inverter to three phase full bridge 120-degree mode. Now we will discuss about last topic, which is related to voltage control. As I told you in the beginning, inverter converts the fixed DC to variable AC. Variable AC can be anything, that is nothing but variable voltage or variable frequency. So that is what we are going to discuss now, voltage control. So for simplicity we are taking the single phase full bridge inverter. Okay, so this single phase full bridge inverter can be represented like this also. In place of SCR, that means in the previous case you can see that. So here we represented this one with SCR only. In place of SCR, it can be any switch. That means it can be represented in the gate exam like this. So don't worry, if it is given like this means don't even worry about that one. So that means here in place of fully controlled switch, it can be anything. It can be anything means it can be BJT, IGBT or MOSFET or SCR. That means in place of this mechanical switch, any of this can be used. That's why this is simply given with the switches only. Now I'm giving three waveforms. Start thinking about like how these three waveforms will give the RMS voltage. That means using these switches I'm generating this type of voltage, this type of voltage and this type of voltage waveform. Okay, all three waveforms will have the same source voltage, nothing but maximum value will be same. Now tell me which waveform will give the more RMS voltage. Is the black one or brown one or violet? Which one? So I hope you are actually thinking about that. But remember, here all three waveforms will give the same RMS voltage, no difference at all. Okay, RMS value of these waveforms will be same. That's nothing but here the RMS value of the any voltage wave, any waveform, any AC waveform will be depending on shape of the waveform only. Okay, it will not depend on that whether it is a medium frequency, high frequency or low frequency. So that's why here all three will give the same. That means using this type of technique you can't get the variable voltage. That means here we are just having a different time period only. So this is a medium time period, so this will have less time period. Okay, so this one less time period, this will have more time period. That means this time period is different for these waveforms, but our voltage will be same. So using this one, what you can do that, it is only simply frequency control. So this is nothing but it's a frequency control. Okay, so this won't give the voltage control. But how to get the voltage control? That's where we are going to discuss. Okay, there are two methods to cut the output voltage, variable output voltage. That's nothing but external control, internal control. What is the meaning of external control? We'll see that. So assume this is a VSI. That means we are giving a constant voltage and we have the some voltage source inverter and we are getting output to the load like this. So there are two different methods we can use the external control further like that. So after VSI, before giving the voltage to the load, we can have one more converter, that is nothing but AC voltage regulator. So here the inverter actually converts the fixed DC to variable AC, and that fixed AC to give into the AC voltage regulator, and that is actually changing the voltage at the required level and providing to the load. So that's one type of method. Another type of method, we are actually using the VSI, but before between the source and VSI, we are having the DC to DC converter. In case of DC to DC converter, what will happen? This fixed DC voltage to variable DC voltage. That means based on the requirement here, we will decide that what should be the input voltage. That input voltage we will control by using DC to DC converter. This is like called as an external method. But look at here, in case of external method, we are having one more additional converter. So if you are having one more additional converter means first of all, it increases the overall size of the converter. So that is actually nothing but bulky and costly, because we need to go for one more converter. Then another thing is, already with the help of with one converter, we are not able to get a complete or perfect AC waveform. That's nothing but a sinusoidal waveform, because it is having or producing some harmonics. If you are having one more converter means more harmonics, nothing but waveform will be distorted. So that means more harmonics due to switching frequency, due to switches. So that means we don't generally use the external control. We generally go for internal control. Internal control is nothing but we will play with the help of switches only. We will not have any extra controller here. We actually, instead of operating the switches in one scheme, we will operate in a different scheme. That's what. Okay, we'll see that what exactly the meaning of that. Okay. So now using this inverter, we are getting this type of voltage waveform. That's we already discussed. It is actually called as a perfect square waveform. This is called as a 180 degree waveform also. This is 180 degree square waveform. That's nothing but how we actually discussed about the switch operation, etc. like that. Now, to get the variable voltage using internal control, we will actually modify that. Means we will get the output voltage waveform like this. That means here thyristor T1, T2 and T3, T4 will be operated such that we will get this type of voltage waveform. That means in the previous case, nothing but in this dotted line, we will actually operate these thyristors for complete 180 degrees. But now we will actually turn on the thyristor T1 and T2 for the positive off cycle at this location, okay, here, and we will turn off those thyristors here itself. Likewise, T3, T4 will be turned on here and will be turned off like this. That means we are operating these switches to get the cos square wave. This is nothing but cos square wave. Okay, so to get the cos square wave, we are not changing input voltage. In fact, what we are changing, we are actually getting the output voltage like this by operating or controlling the switches. So that's why it is called internal control. We are not doing any external converters and all. So that's why. So this width will be, assume D. Okay, pulse width. D radians. So now if you get the RMS voltage using our initial equation, remember we discussed in the beginning, RMS value of this one is, this is a symmetrical waveform. That's why you can take half of the waveform, then square root of RMS value of this segment is nothing but it is a square wave. So VDC square and multiplied with the available duration T, and here this segment is 0, this segment is 0. That's why total divided by pi. So V square comes outside as a VDC and root of D. So now here output voltage of this waveform is depending on width of the waveform. If you are changing the width by controlling the switches, you can actually get the variable output voltage without changing input voltage. So that is the one of the control technique. Okay, so if you take the D equal to pi, that means this pulse width is entirely 180 degrees, then you will get the VDC only. That's nothing but 180 degree square wave mode. So this is the one type of technique to control the output voltage. So to control this output voltage, we are changing the D. That's nothing but width of the pulse. That's why this is called pulse width modulation technique. That means we are controlling this output voltage by using the pulse width. That is why it is called pulse width modulation technique. Okay, remember that. So here, how many pulses we are using to control the output voltage? Only one pulse per an half cycle. That's why it is also called as a single pulse modulation technique. Okay, we'll discuss some more things about this one. So if you take that this waveform as it is, and then I'm representing the pulse width D, and this quasiness is nothing but alpha here, so 2 alpha, and this waveform is symmetrical about 90 degrees. Okay, so using this, if you take the Fourier series for this one, then we will actually discuss further things. Fourier series means, as I told you, that for any square wave we will have only odd harmonics. Okay, so V naught equal to sigma n equal to 1, 3, 5 and so on infinity, and for any square wave we will have 4 by n pi multiplied with maximum value or amplitude, that's nothing but VDC, and this is sine n omega t, because it is a symmetrical about 90 degrees, that's why you will have sine n omega t, and remaining thing we can represent with the help of pulse width or with the help of cosinus, but pulse width is here d, we need to take half of that, so that's why sine n d by 2. Similar thing we can represent with the help of cosinus, that's nothing but same thing, but in place of sine we'll have cos n alpha, so that is the difference there. Okay, and we already discussed V naught. What is the V naught? So V naught is nothing but, so V naught RMS I'm talking about. V naught means V naught RMS we already discussed, that's nothing but VDC into root of d by pi. Okay, so remember these things, we will again come back. So continuation to this single pulse modulation technique, I am taking further and this things in this, that's nothing but like you can consider fundamental voltage. If you take n equal to 1, you can substitute here and you will get the fundamental voltage waveform. So fundamental voltage is nothing but 4 VDC by n pi, n is pi 1 and pi only, you will see that, and sine d by 2 and sine omega t. So this is the time quantity and rest of the things comes under max value. So now if you want to calculate, this is a sine wave, if you want to calculate the RMS value for the fundamental voltage, we need to take V01 equal to maximum value divided by nothing but 4 VDC by pi into sine d by 2 whole divided by root 2. Okay, so further simplification, this will give that V01 equal to, this gets cancelled to root 2 times, 2 root 2 by pi is nothing but 0.9 we discussed, so 0.9 VDC into sine d by 2. Okay, this is the fundamental voltage RMS value. We already discussed RMS value of the total system, total waveform including harmonics, that is V0, V naught RMS. Once you know that, we can calculate distortion factor, percentage TH rate, etc. For that we need to have this one, fundamental voltage. Okay. Then we need to look at other things here. Likewise, you can calculate third harmonic, fifth harmonic and all. Anytime if you are getting negative value of this one by substituting the required D, take it as a positive. Okay, remember that. Now, using single pulse modulation technique, mainly pulse width modulation technique is meant for only voltage control. Okay, mainly for voltage control. Understand? So this is mainly for voltage control, but on top of the pulse width modulation, on top of the voltage control, by using pulse width modulation technique, we will get some advantage. That advantage is nothing but by setting the proper pulse width, we can eliminate some harmonics from the output. That means certain harmonic in case of single pulse modulation technique. That means how to do this and all, remember here. So substitute n equal to n. In this, n equal to n is nothing but nth harmonic component. So what is the nth harmonic component? Substitute n equal to n here, that's nothing but V0n is nothing but, so 4 VDC by n pi sine nd by 2 sine n omega t. Okay, this is nth harmonic. So assume you want to eliminate the nth harmonic from the output. In that case, we need to make this 0. If you want to make this 0, then this is a constant, will not be 0. This is a time quantity, this never be 0 continuously. It will be 0 at some occasional points only. That's why this will not be 0 permanently. Then remaining thing is sine nd by 2. Okay, so we know that sine sine equivalent solution, that's nothing but you can see the general solution. So nd by 2 is nothing but m pi. Okay, because n already we consider, so m pi. So we know that, we remember, maybe like we discussed in the rectifiers, if you remember that sine theta equal to sine x. What is the general solution here? Theta equal to n pi plus minus 1 power n into x. So that's what here. In place of n, I am taking m here, m into pi, because here n is already taken for harmonic content, that's why. Plus minus 1 power m, here m is, m, okay, into x. X is here because this is like a sine 0 is 0, so that's why I'm taking x equal to 0, means this will be 0. That's why you will get m pi. From this, what is the pulse width required to eliminate the nth harmonic from the output of this waveform? That's nothing but 2m pi by n. Okay, so remember this is important. Okay, and here d is nothing but pulse width to be set to eliminate nth harmonic from the output, and m is nothing but, it is integer 1, 2, 3 and so on. Okay, and n is nothing but harmonic number to be eliminated. For example, you want to eliminate third harmonic from the output. So third harmonic you need to eliminate means we need to substitute m equal to 3 and m equal to 1 for first time, and calculate the d. D is nothing but m equal to 1, that's nothing but 2 pi by 3. So 2 pi by 3, nothing but, if you set pulse width is 120 degrees, then output will not have any 3 and triplet harmonics. That's the meaning of this one. Suppose if you substitute m equal to 2, then it is 4 pi by 3. 4 pi by 3 is 240 degrees, but D maximum value is 180 degrees. Maximum value of the D is 180. That's why to eliminate the third harmonic from the output, you will have only one option. Suppose if you want to calculate pulse width for fifth harmonic elimination, that means n equal to 5. If you want to do that, means substitute m equal to 1. M equal to 1 means 2 pi by 5. Okay, 2 pi by 5. Okay, 2 pi by 5. So that's the one thing. 2 pi by 5 means 360 divided by. Okay, so that's the one. So then D equal to, substitute m equal to 2 here. M equal to 2 is nothing but, it is like okay, so 4 pi by 5. So this is nothing but, to eliminate the fifth harmonic, we will have a kind of like two options. This is nothing but, okay, so 360 by pi. 360 by pi means how much it is? It is 72 degrees, and this is 144 degrees. Okay, both are less than 180. That's why you can take these things, either setting 72 degrees or 144 degrees, you can actually eliminate fifth harmonic. Likewise, we need to calculate. Okay, remember that. That means using single pulse width modulation technique, we can vary the output voltage. At the same time, you can also eliminate certain harmonic number by setting the proper pulse width. Moving on. So here we already discussed, like by setting the pulse width, we can also eliminate the harmonic number. Okay, that's what we discussed. Now here, if suppose instead of pulse width, we can also represent the same thing with the help of alpha also, but it will give you only one value. That means if you want to set the alpha to eliminate the harmonic, nth harmonic, that means we need to take 90 divided by n. N is nothing but harmonic number to be eliminated. So here, if you want to eliminate the third harmonic, n equal to 3, in that case, alpha to be set is nothing but 30 degrees. Okay, we already discussed something like this, like we need to have the waveform like this. Okay, so this is 180, this is 0. So this is the pulse width we are talking about, T, and this is alpha, this is alpha. So alpha is 30 degrees, means this is 30 degrees, this is 30 degrees. Out of 180 degrees, 30, 60 is taken out, remaining will be 120 degrees. Okay, so that is what we already discussed. 120 degrees pulse width if you set, then third harmonic will be eliminated. Okay, third and its multiples, like that. So you can also set the like alpha to eliminate certain harmonics by using this formula. Okay, remember this one also. Okay. Okay, good. So, but how to control these waveforms, like how to control the switches to get this type of waveform, that is what we are going to discuss. How to generate the pulse. To generate the pulse, we generally take the carrier waveform. Carrier waveform is nothing, most of the times triangular waveform we will get that. This waveform will be given to the comparator, nothing but op amp. One of the input to the op amp will be this one. Then we will actually take the reference voltage, reference wave. That reference wave is nothing but square wave. That square wave will be given to the second input to the comparator. So whenever square wave is, or reference wave is more than carrier wave, we will generate pulse. Okay, whenever, that means you can see that during this period reference wave is more than the carrier wave. In that case we will generate pulse. Okay, here you can see that negative side, this is more than this one, that's why generating pulse. This input we will give it to the switches to the inverter, nothing but SCRs. Whenever the pulse is there, we need to turn on the respective switches. Whenever pulse is not there, we need to turn on those switches, like that. So we will get. But you may ask the question here, we are able to generate this type of waveform, why do you need to go for the inverters, etc.? So remember, this we are generating using any microcontroller or like that. This is very, very low voltage. It is generally 5 volts, current is milliamperes. But output of the inverter we need to get, which is like kind of very high voltage and very high current in kilovolts and kiloamperes also. That means we are generating this type of pulses in the very, very low voltage to replicate the same thing on the output of the inverter. So we are operating the switches such that to get the same type of voltage waveform in high voltage and high current by using switches. Remember that. Okay. So there is another important here, the amplitude of the reference wave. The amplitude of this reference wave is VR and amplitude of this carrier wave is VC. The ratio, most of the times, to control the pulses, either increasing this pulse width to increase the output voltage, or to decrease the pulse width to decrease the output voltage, we need to control these waveforms such that, okay, to do that one, we will actually take one important one, that is nothing but it is a modulation index. Modulation index is nothing but it is the ratio of reference voltage amplitude to carrier wave amplitude. Most of the times carrier wave amplitude is kept as a 1. Okay, that's a fixed. We will, to change the pulse width here to get the different voltage at the output, we will change only amplitude of the square wave. So that's what we will control the output voltage by changing the pulse width. Nothing but modulation index. Okay, you can see that. Suppose if you want more output at the maybe for example low voltage you want. Low voltage is nothing but very low voltage you want. How to get the low voltage? We need to change the pulse width of the output voltage. If you want low, means low pulse width is required. You can see that. If you reduce this amplitude of this square wave, you can see that pulse width is reduced, such that you can get the low voltage. If you want to get the output voltage more, then we need to increase this amplitude of the square wave, and then you can see that it is increased. Now I have taken complete one, like that means modulation index is 1, means you will get the perfect square wave. Okay, so both the waveforms amplitude is same. In that case, you will get the proper square wave. That means we are operating the switches for complete 180 degrees, like that. So we will change this one. Okay, so this is called single pulse width modulation technique. Again, I'm telling that pulse width modulation technique is required or meant for only voltage control. But by using this pulse width also, we can actually get the kind of elimination of the required harmonics. But remember, with the single pulse modulation technique, we can be able to eliminate only one certain harmonic and its multiples. We can't eliminate all the harmonics. To eliminate more number of harmonics, what we need to do? We need to do multiple pulses. That means in earlier we have only one pulse per an half cycle. Okay, for an half cycle, one pulse. That means switches like the T1, T2, T3, T4, we are operating only one time in a given half cycle. But if you want to eliminate more number of harmonics, we need to go for multiple pulse modulation technique. Here we will take the same carrier waveform, same like square waveform, but to get more pulses per an half cycle. In this case, same technique, nothing but whenever the reference wave is more than carrier wave, we will get the pulse width like this. So same, but instead of getting only one, we will get more pulses here. In this case, 3 pulses are there, means each pulse width will be same. Okay, width of each pulse will be same. This is actually total pulse width is D. That means this is D by 3. This is D by 3. This is D by 3. Okay, and here we will get the like a equidistance pulses. Distance between each pulse will be same. So using multiple pulses, we can actually eliminate more number of harmonics. More number of harmonics can be eliminated. Okay, by selecting the pulse width and the distance between the pulse width. So based on that, here you have the 2 degrees of freedom. One is pulse width, another one is distance between the pulse width. So that's why you can eliminate more number of harmonics without using the filter. That is what actually we can do in the multiple pulse modulation technique. But remember, in case of like we are comparing that carrier wave with square wave. If you compare with the square wave, you can get the equidistance pulses. That means distance between each pulse is same, and equal pulses. That means pulse width of this pulse, this and this are same. In that case, we can't eliminate more number of pulses. Sorry, more number of harmonics. If you want to eliminate more number of harmonics, instead of square wave, we need to go for sine wave. If you go for sine wave like this, you can see that we are getting the pulses, but those pulses are actually, you can see that width between the pulse is different and width of the pulse is also different. Generally, this width of the pulse just will start from the starting, will be like a kind of, you can look at here, it's like a kind of like from the starting it will be very small, and then while going towards maximum you will get more like a bigger pulse. Understand? So that's what. So this type of voltage will be, pulses will be given to the thyristor T1, T2, and these pulses will be given to the thyristor T3, T4. So you will get the output voltage like this. Whenever you are operating the switches like this, you will get this one. Okay. So more pulse width, like a positive value is more, positive value is less, negative value is more, positive, like that means you will get the, like using the filter, you will get the sine wave like this. So here the main advantage of this sine wave, this is called as a SPWM also. Most of the times people will call it as a SPWM. SPWM is nothing but sine wave PWM technique. Okay, so SPWM. So here you can see that this width of the pulse is different. That's the first thing. And distance between each pulse is also different. That is why you can eliminate more number of harmonics, and this is a popular technique. But in sinusoidal PWM technique, we have two type of techniques. One is bipolar PWM technique. This is bipolar. You can see that voltage levels, output voltage level is changing from positive to negative VDC. Positive VDC to negative VDC. That's why it is called bipolar. But in this case, we are actually using the sinusoidal PWM technique, but we will operate the upper switches with this waveform, lower switches with this waveform. Okay, lower switches. So in that case, we will get only one type of voltage in the off cycle. That means positive voltage in this one, and in this one negative VDC. This is called unipolar PWM technique. Both are sinusoidal PWM technique only, but this is bipolar, this is unipolar. Okay, so we'll have some advantages of each one. So in this case, more harmonics will be there. In this case, less harmonics will be there. And that's the one thing. Second thing is, like you can see that suddenly changing from positive VDC to negative VDC means this may have, like from the same leg, both the thyristors are having the transition. Here also transition. If this transition is not happening properly, if it is delayed, then source will actually get short circuited. In that case, switches will be damaged. So that's why most of the times we will go for the unipolar. Okay, in both the cases, we will have one formula to calculate the output RMS value and all. We have only one formula, remember that. So this is a big derivation. We are not concentrating on the derivation, but we need to remember. Output voltage, fundamental voltage, max value only we can calculate using source voltage. This is for applicable for single phase full bridge inverter VDC into modulation index. So this modulation index, remember, can be represented like this, amplitude ratio, ME also. Okay, don't confuse. So if suppose if you want to apply this one for the single phase half bridge inverter, then in place of VDC we need to take VDC by 2. Okay, that is what. So in case of sinusoidal PWM technique, in any of this case, okay, both you can use. Fundamental voltage maximum value, remember this is not RMS value, maximum value. That means amplitude of the fundamental voltage is source voltage VDC into modulation index. Modulation index, as I told you, that reference voltage magnitude divided by carrier voltage and magnitude. Okay, amplitude. So that's what you need to remember. Okay, so but there is another thing here. Why are we using the pulse width modulation technique in any case, like either sinusoidal or square wave? So to eliminate, main thing is to control the output voltage. Pulse width modulation technique is mainly for voltage control. But on top of that, by selecting the pulse width and distance between the pulse width, nothing but by changing the modulation index, etc., we can eliminate the lower order harmonics. So elimination of the lower order harmonic with the help of filter is very difficult. That's nothing but we need to have high inductance, high capacitance. That is actually costly and bulky. That's why we will eliminate the lower order harmonics with the help of PWM technique, and higher order harmonics will be eliminated from by using filter. Or suppose simple thing, single phase system will have order of the harmonics like third harmonic, fifth harmonic, seventh harmonic, ninth, and so on. You will have suppose 101, 105, something like that. So these are all called as a lower order harmonics, and these are all up to infinity called as a higher order harmonics. Higher order harmonics will be eliminated using filter. Okay, this has to be eliminated using PWM technique. Otherwise, to eliminate these harmonics is very costly with the help of filter. So that is the additional advantage we can able to get with the help of pulse width modulation technique. So if you are increasing number of pulses per half cycle, then you can eliminate more number of harmonics. But if you're actually increasing more and more pulses in each off cycle, means we need to turn on and turn off the switches. That means switching frequency will be increased. Switching frequency will be increased is nothing but loss in the switches will be increased. That is why we need to treat the trade-off between, if you're increasing the number of pulses, how much power lost is there in the switches versus how much cost we are saving by reducing the filter requirement. We need to take that. That is why this pulses per an off cycle will also be limited. It will not be infinity. Okay, remember that. So as I told you, like a practical circuit, how the practical circuit will be there. So you will have an inverter here. So inverter will convert the DC to AC, but most of the times we'll have this one only. What's that? Square wave. So to filter out all the unwanted components from this, we will use the PWM technique to filter out the lower order harmonics, and remaining higher order harmonics will be filtered out by the filter. So that's nothing but low pass filter, LC filter. So once you filter out this one, you will get the sinusoidal waveform like this. So with this, I'm stopping here. If you have any questions or anything, let me know through the mail or comments. We'll discuss accordingly. Thank you.